I'm Bruce Bugbee, president of Apogee Instruments and also professor of crop physiology at Utah State University. In this video today, we're going to talk about the basics of lighting as it applies to cannabis. This is profoundly misunderstood. The database is filled with a lot of myths that we have studied over the past year. And so we're calling this Cannabis 101. This first part of the series is just focused on lighting, which is one of the key parameters. Apogee has spent decades refining instruments to quantify light, the types of light, the intensities of light. Those, in my experience, those instruments are underutilized to help refine the cultivation of cannabis. And part of it is just because people don't know how to interpret the data and how to make the measurements. As a company, Apogee Instruments' motto is, we help people make measurements. And part of that is our ongoing education to help people interpret the data that they get, make sure the measurements are high quality, and that's what this video is about, with a focus on cannabis. We're not focused on all the other crops like lettuce that's grown under electric lights, just cannabis. Utah State University is one of the few agricultural universities that now has a license to study hemp at the university. And when I say cannabis, I mean both hemp and marijuana. Our license isn't for marijuana, it's only for hemp, but the studies apply to both types of cannabis. So I'm going to talk about cannabis in this video. So it's pretty hard to underemphasize the importance of light when you're growing a crop. And this next slide, which I've used many times in many talks, really focuses on that. Here's the 9 cardinal parameters. If you were to take a university class, you would be reviewing each of these parameters. 4 of the parameters are in the foliar environment: temperature, humidity, air velocity or wind, and carbon dioxide. 4 are in the root zone environment. We have temperature down there, amount of water, nutrients, and oxygen. We teach whole classes on each one of these parameters, and we may do a series on cannabis on each one of these parameters, but today we're going to focus on the one that is absolutely critical, and that's light. And we put this right at the top. Let's see if this, see if we can get this back. Pen tool. And then let's go to pen tool. There we go. Light, and let's see if we can get that yellow to emphasize the light. Light is coming in from all directions on this plant, and it drives the optimum levels of everything else. If you turn the light up, you have to give the plants more water because it drives the flux of water through the plant. I should have drawn this in yellow or in blue for water flux through the plants. You turn the light up, you need more nutrients. You need more oxygen in the root zone. It drives everything. So often we get questions from people saying, my light must be too high, my plants are turning yellow or purple or some color. What it really is an imbalance between the amount of light and the optimum levels of all these things. It's like a race car. Cannabis is a race car that can go incredibly fast. If everything is optimum, you can give cannabis exceptionally high levels of light, and I'm going to go into how we measure that and quantify it, if all of these other parameters are also optimum. If you give it more light and you don't have the right nutrient balance or the right water, or you don't have elevated CO2, you're going to have problems with the plant. But it's not fundamentally caused by the light, it's caused by inadequate levels of the other parameters. Be like a race car and saying you got a giant engine, you're out at the Utah Bonneville Salt Flats, you're going 700 miles an hour, and the tires blow on the car. And you say, ah, dang it, the engine was too big. No, the engine wasn't too big. You didn't have the right tires for that big of an engine. That's the analogy of how important it is to get the lighting right. So, let's start with how we even measure light. So many people say, how much light do I need? And they'll say, oh, keep your plants about 30 centimeters, about a foot away from the lights. Let me show you how bad that is as a measurement of light. And in order to do this, we have set up here in the Apogee studios 2 lights of different wattages, and I'm going to do a demonstration now to show you how important that is. So I got to step over here and plug the light in, wheel this in. Now, here's 2 lights. Let's get them right in the screen. 2 different wattages of lights. They're both LEDs. I could turn them toward the screen. It'd be incredibly bright. Now, we've set this up so we can measure. If I can do this right there, we can measure the intensity of the light from these. Here's the number right here. We'll get into what this means in just a second. But it's 27 micromoles of photons right now. That's the light from the studio. If I put this over here, 7. Now 7 is plenty of light for humans to work in. A well-lit office has 7 micromoles. That is way too low to grow cannabis. You can tell these are a little brighter. What if we said it's 7 here? How bright is it over here? Oh, it might be 50 over here. Let's take a look. We're going to go under this light. Now let's see if we can do this. Can you see the screen? I think you can. I'm going to hold this right here, about a foot away. You see the number we're getting? 300 micromoles. A well-lit office is 7 to 10, and this is 300. So, and it looks a little brighter, but it doesn't look 20 or 30 times as bright. It's much, much brighter. That's a foot away. What if that was our measure for cannabis and we say, here's another light, let's go a foot away. Now we put it under this light. Look at this. I got to get it centered. 3,000. Depends on exactly how far away, but we're approaching 3,000 micromoles. If I go a hair closer, there it is, 3,000 micromoles under this light. And we go under this light, same distance, we're down around 300. That is almost an order of magnitude more photons under one light than the other. And the only difference is the input wattage. This is a low input wattage, this is a high input wattage. It's not color of light, it's input wattage. So I hope you can see that just saying put your plants some distance away from the lights is a very inadequate way to precisely grow cannabis. You've got to have a meter. Our eyes are one of the worst meters for plants. Our pupils contract to reduce the amount of light getting to our retina in bright light. So we're a terrible light meter in terms of intuitive estimating of light. We really need an instrument to measure it. So this is a demo of the fact that you can't do that. Now, remember that number. Let's take 300 micromoles, and how much cannabis could we grow with that? Now I'm going to stop here and take these out of the way and so we can interpret the data. Now we're back with a white screen that we can take a look at what we just measured. So first of all, let's draw what we call a light response curve for plants in general, and then we'll draw a light response curve for cannabis. So, as students in my classes know, over the years I draw a lot of XY plots to take an input variable here and look at response. So what we're going to put over here is PN. This stands for net photosynthesis. And over here, we're going to put PPFD, photosynthetic photon flux density. That's what we just measured with that Apogee meter. This graph starts at 0 here and 0 here. If this was Introduction to Plant Science, and we asked this question, everyone would say, well, of course, light or photon flux drives photosynthesis, so that curve is going to look like that. And if this was Plant Science 101, we would count that as a correct answer. But if it's a more advanced class, we know that the higher the light, this doesn't keep going up forever. Plants can't keep using all those photons, so a more correct answer looks like this. And we can even erase this top incorrect answer and go back to this. There's a more correct answer because it levels off at high light. Now notice, I didn't put any tick marks on here yet because we just measured 300 micromoles and even almost 3,000 out of that other light. But there's one more thing that makes this curve even more accurate, and I'll put that in blue. If you take a plant and put it in the dark, it gradually respires and dies. You can't keep it in the dark for weeks or months. So this line doesn't go through 0 right there. In the dark, we get a negative number. The plant is shrinking, it's dying, and we turn on the lights and it goes like this. So there's some point right here where there's just enough light to keep the plant alive. This, by the way, is called the light compensation point, when there's enough light to get it to 0. Now let's put some tick marks on this axis. Photosynthesis, let's make this go to 60 up here. By the way, the units for this are micromoles per meter squared of leaf per second of time. This is how fast it's fixing carbon in dry weight. Now let's put some tick marks on this. If we go up to here, what's full sunlight? If we went outside in the summer at noon, what would we get for high light? We would get 2,000. That's an important reference point, 2,000. These units are micromoles of photons per meter squared per second. And this could be over here, could be just yield of the plants. But these are the units that we're measuring to get the light. Now if that's 2,000, 1,000 is right here, and 500 is right here. On the way I drew this graph, wow, we have to have 400 micromoles just to get above 0. Now, this only happens in a dense crop. But let me see if I can erase this, erase these lines, and I'm going to draw 2 lines on here. Let's go back to green. We're going to fill this back in. Here's our green. There's 500. Now let's go to blue. If we did these measurements for lettuce, lettuce is a widely grown crop, very widely studied. It is also a low light plant. Lettuce grows fine in much lower light than cannabis. So if we draw a curve for lettuce, first of all, it starts here. It goes up, and at about 500, Lettuce is done. And it might even go down out here at really high light. This is lettuce. There. Now, what if we put cannabis on here? Cannabis is life in the fast lane. It takes a lot of light. You can grow lettuce or grow cannabis much faster. We're going to put cannabis in red. First of all, doesn't really have a low gear. It has a high respiration rate. Cannabis looks something like this. Look at this curve. Look at that curve. Wow. This is cannabis. It keeps going up until 2,000. So cannabis is a very high light crop. You can give it a lot of light, but you've got to have all the other inputs optimized. For sure, you need elevated CO2 for cannabis, and ample water. It's usually automated watering. It's a balanced nutrient solution. That's a topic of a whole nother talk, but our data don't indicate cannabis needs unusual nutrients, but it needs a balanced nutrients and not too much. Usually there's toxicities from too much nutrients, and if you have this high light and the water's going through the plant that fast, you have to be careful not to have too much nutrients. But the point is, look at cannabis. Corn is like this too. Corn is a very high light field crop. So now we get a meter to measure this, and if the leaves are green, we're using the photons efficiently and we have high photosynthetic rates. Let's take a look on this now, a closer look at this unit down here. This is generally a widely used unit, but it's not universal. And let's take a look at this. And I can do that on the next screen. Now let's go back to green. Multiple acronyms are used to measure light. And the most common one is PAR. That stands for, the P always stands for photosynthetically active radiation. Let's go to a slightly smaller line size. That's a pretty fat line. All right, now we've got a PAR. This is a generic term for all photosynthetically active radiation, but it could mean watts per meter squared, and that's confusing. So a more rigorous term is PPFD. That stands for photosynthetic photon flux density. And this always means that number from the previous one, moles of photons. And you think of photons as like tiny little marbles falling out of the sky to fill a box. They can be colored marbles, but they're all marbles. We're measuring this flux of photons coming into the plant. Per meter squared, per unit area of surface area, per unit time. And we always use per second. That's the unit for PPFD. Now, this is a big number, a mole, and so it's really a micromole, 10 to the minus 6 moles per second. And this number ranges, and we just showed that in the other slide, 0 up to 2,000. It's a huge range. Remember those lights we measured? One was 300, one was over 3,000 because it was a high wattage light and we're real close to it. These are the keys. Now we'll come back to this later, but PPFD is the number that we're after here for light. Now let's go to another screen. We're gonna take our same screen here, and we had PPFD 0. Let's go all the way to 2,000. This is very bright light. We rarely get this high of light under electric lights, but we could. And over here we're just going to put yield. Not photosynthesis anymore, because photosynthesis leads to yield. How much light is necessary? What's really key about this is not the instantaneous light. We're going to put our graph on here again. Something like this. The exact shape varies with different cultivars, but it doesn't vary very much. It turns out it's not exactly the PPFD, it is the DLI, daily light integral. So as this implies, an integral means we add up all of the photons. This is per second, and every second we accumulate them. What if this was rainfall? PPFD would tell us the rate. How fast is it raining per second? But usually what we want to know is how much did it rain yesterday, the total amount of rain. And that's the daily light integral, called DLI. Let me show you how to convert. Once you see this, you'll know it forever. Let's put 1,000 in here. We're going to convert from PPFD to DLI. 1,000 micromoles per meter squared per second. Now we want to know per day. Well, there's 3,600 seconds per hour. So this is 3.6. Now notice, this is 1,000 and that's 3,000. And when you multiply these together, the thousands cancel, and this is 3.6 moles. Now, no micro anymore because we just multiplied two big numbers together. 3.6 moles per meter squared. Now, this is per hour. We're still not there. That's per hour. For cannabis, when it's in the flowering stage, we would typically give it 12 hours per day. And we multiply these two together, 3.6 and 12. I know this because I've done it so many times. That comes out to be 43.2 moles per meter squared per day. And that number right there, this is so important, we'll put it in red, is the DLI. If you had 1,000 micromoles per second continuously for 12 hours, you get 43 a day. This is high light, but cannabis responds to this. In our studies, we can push them even higher than this. We've never gone to 2,000, but we've gone close to it. We've gone to 1,800, up to where we've gotten this number close to 60. Outside, in the summer, under full sunlight, on sunny days, DLI can get to 60 moles per meter squared per day. That's an incredible DLI. Cannabis grows outside in full sunlight, and it loves it. It responds to it. So you can run the DLI up extremely high. Now, how low can you go? Well, here'd be 500. And you see the point here. There's some diminishing returns. It's still, the line still goes up, but it's curving over. So 2,000 doesn't give us twice the yield of 1,000, but it's still higher. So we keep raising this. There'd be 500 right here. But the point is, you've got to get this, you've got to know this input to have reproducible studies, and to get it, you need to measure it. Let's take a second to look at, review some of the instruments that Apogee uses. All of them are a little sensor here. The quantum sensor is blue. That's the one we used a minute ago to measure these. This one plugs right in to a laptop. Here's a USB cable, and we can plug right in. You got to remember to take the cap off of these. The optics here are really rugged, but we still ship them with the cap to keep them perfect. Plug this right into a laptop, just like I did, and you'll see the numbers on the screen. If you want something more portable, here is a handheld meter with a separate sensor. These also come with the sensor right in it. That's another option. And one of the options that's big and catching on fast is Bluetooth. This is a Bluetooth module. It's like a data logger. It measures and stores the data, and then you just transmit this data right to your cell phone. So this is a powerful option. There's plenty of graphics associated with this for measuring the light. All of them go to this sensor. If you jump up another level, this gold cube is a spectroradiometer, which gives you all the ratios of colors. But these other instruments are down in a few $100s. This instrument is over $2,000. This is much more sophisticated, but this is what researchers use to get everything exactly right in all of these. So we get questions all the time on issues relating to light. And I just addressed one of them, daily light integral. We can push daily light integral easily to 30, to 40, to 50, and the yield keeps going up if everything's optimal. In terms of how much light it tolerates, this is true even for young seedlings. We once took, one of our research projects right now is to push the rooting of cuttings of cannabis with very high light. This just sounds amazing. For years and years we'd keep plants in really low light with cuttings because they didn't have any roots. We're finding if we can keep them watered, we can even push a cutting with very high light levels. And certainly a young plant, you can push them hard with high light. Again, as long as the other inputs are not limiting growth. What about darkness? Let's go to another screen. Another topic. We'll put this one in blue. Now we're going to do hours per day. It's a different graph. Hours. Here's noon. Here's midnight. And here's midnight. And of course here's PPFD. We have no evidence that suddenly turning on the light shocks the plants. They can get out of bed and go right to work. They don't need to ramp up slowly. But let's say we turn on the lights at 6 a.m. We run them high until 10 p.m. If we ran them this would be a 16 hours of light. Now if we're in flowering phase, let's go back to red. If we're in flowering phase, we might run them from 8 a.m. to 8 p.m. like this. And this is a 12-hour photo period. So there's really just two photo periods for cannabis. A 16 and even an 18-hour photo period for veg. And in fact, some of our data indicates this could even be 24 hours for veg. Just get the plants growing with a high DLI, and then when we want them to flower, we switch to 12. Now, here's the question. So this is all fine. What about right here? This number right here is darkness. How dark does it have to be for cannabis at night? This is something we're actively studying right now in my laboratory at the university. There are some literature reports that indicate that cannabis is exquisitely sensitive to trace amounts of light pollution. Just a little bit of light will cause problems with cannabis. We have a wealth of literature on poinsettias. They're one of our most sensitive crops to light pollution. Without excellent darkness, those top leaves of of cannabis don't turn red. They're called bracts. They don't turn red. Is cannabis more sensitive than poinsettias? We don't know yet, but we know it needs to be very dark. We call this reagent grade darkness, and it's like somebody sleeping. Some people are bothered by a tiny light sleep, and other people doesn't matter. But we think cannabis is quite sensitive to this. For this reason, Apogee has made a extended range quantum sensor that's calibrated to rigorously measure light pollution. Now remember, we were doing micromoles per meter squared per second, and we were getting numbers in the hundreds. This particular sensor can measure 0.01 micromoles per meter squared per second. It's a unique meter that can detect trace amounts of light, and it helps you determine whether it's absolutely dark. It's a extended range sensor. Even picks up the photons from security cameras, which there's possibilities for those to affect cannabis. That's a topic for another video. So, extended range quantum sensor for light pollution studies. This is getting down around full moonlight, and we know that full moonlight doesn't affect cannabis or any other plants, but it might not take much more of that to be a big deal. Let's talk about cultivars differences. Many people say, gee, this happened in one and something else happened in another. We have an emerging number of different cultivars for cannabis. As you probably know if you're watching this video, I won't write them up here. They're all cannabis sativa, and underneath that we have indica and sativa. So it's cannabis sativa sativa. Our studies at the university indicate there's definitely differences in those, leaf width, leaf size, but in terms of response to all these parameters I'm talking about, there's not a significant difference between the types. You can push both types of cannabis with highlight. They both love highlight. They both evolved out in the field. The differences can be in yield. They can be in photoperiod sensitivity. Some cultivars of cannabis we think can take 13 hours of light over here. Some might be able to take 14, but in terms of pushing them with highlight, they're all similar. Let's think about some of the other cultivars. One of them, some of the other questions we get. One of them is, what about light quality and the synthesis of what we call cannabinoid compounds? That's THC, CBD, CBN, CBG, all the different cannabinoid compounds. Then in another class of compounds, there's terpenes. What about light quality? And it could be a whole nother talk, and I have given other talks on this. They're in other videos on the Apogee website. So if you're interested in this, look for other videos on this. Here's the take-home message. We don't have evidence that changing the colors of light makes a significant difference on cannabinoid synthesis. Let me say that again. This is an amazing statement. Light quality does not have a huge effect on the ratios of cannabinoids. This is in spite of many people claiming it does. Our data in general don't support that there's big effects. I didn't say there was none, we just don't see big effects. We're still actively studying that, and stay tuned because we're looking at all kinds of different ratios. Now, let me conclude on one part of light that is enormously important. And we're going to go to a new screen. Last slide. I don't like to draw those. I'm going to draw the axes in blue. This is 400 to 700, and this is the wavelength of light. If you're going to get a degree, an honorary degree in cannabis science, you got to memorize these two numbers. We use lambda to express this, and the unit here is nanometers. So this is colors of light. This is what you would use this spectroradiometer to measure. So I think most people know, but let's review this. Right here, if we do 500 and 600, this area right here, 4 to 500, is blue. It looks blue to the human eye, and we call that range blue. Now we go to 5 to 600, and that range is green. And now we go to 6 to 7, and that range is red. For many of you, this is review, but it's important to have the basics. All right, photosynthetic radiation stops right here. Our historic and classic definition of this is 400 to 700, period. If there's a photon at 701, we don't count it. If it's at 399, we don't count it. Is that right? Really? They chop? No, they don't chop off like that. We've known that for years. This is just a useful approximation of photosynthetic radiation. But now that we have LEDs, that we can fine-tune all these wavelengths, we are re-examining what we have used for half a century. And there's two specific wavelengths that are huge. I think I'm still on red. Right here, no, let's go to red. Right here, this is far red. If I can get that up here. FR, far red. That is out here to 750 nanometers, this zone right here. Our eyes have trouble seeing this. It's just like a dull glow of a red burner on a stove, of an electric burner. You couldn't really read a book by this, but it has powerful effects on plants, and it adds 750. Our data indicate that these photons cause photosynthesis, and they certainly cause changes in plant shape. We can make plants branch more, we usually make them taller with more far red, but these photons are critical. Because of that, well, before we get to that, let's talk about the other end down here. Blue, these photons, especially 350, 300 nanometers, this, of course, is all ultraviolet. Our eyes don't see this. Historically, electric lights, we try to get rid of this. They're not useful for human lighting, but they have powerful effects on plants, especially this region at 350 right here of UV. Our data indicate these photons cause photosynthesis as well. So I think we're going to see an emerging change in the definition of photosynthetic radiation, maybe from 350 to 750. We'll see. Multiple laboratories are studying this. Because of this, Apogee has come out with what we call an extended range quantum sensor. And that is a sensor that measures everything from 350 way out here. It picks up, here's security cameras. They have a big peak out here. That's centered around 830 nanometers. That extended range picks up all these photons. And for some kinds of lights, these photons are critical. You want to know what they are. Even though the classic quantum sensor doesn't include them, the Apogee extended range quantum sensor does include them. So UV photons have the potential to reduce disease in plants. They have the potential to trigger cannabinoid synthesis in plants. So we're putting a lot of energy into studying the potential use of UV photons into plants. Again, stay tuned. And one more thing. We get a lot of questions about optimum ratios of colors for both growth and photosynthesis and for cannabinoids. And let me fall back on the one principle here that has guided us And that's the percent blue photons. And let's do this in a different screen. Here's my marker. For years, before we had LEDs, people said, you want to do metal halide for veg, VEG, before they became reproductive. And you would typically be giving, maybe even an 18-hour photo period during that time, during veg. Then the prevailing wisdom was to switch to high pressure sodium during the reproductive phase. And that's flowering. Now, many people said, oh God, that's all a myth, and not exactly. Metal halide has 30% blue photons. This is having trouble. 30% blue. Those blue, the higher the blue photons, the more compact the plant. So metal halide was very effective at making nice compact plants. High pressure sodium, on the other hand, only has about 4% blue photons. Sunlight has about 30% blue. They switched to high pressure sodium because it's a much more efficient light and you can get bright intensity, but it had low blue. But the blue didn't matter so much during flowering because the flowers kept the plants short. So there was a reason to go with a high blue light during veg and then a very efficient light during flowering. And we've seen that in cannabis. It's a ratio of blue photons for plant height and then the efficiency of the light after that. So what we like to see are very efficient lights. The ratios of colors are less critical. We do like to see lights with enough green photons so you can diagnose plant disorders. Those green photons usually come from white LEDs. It's important to look for microscopic insects, subtle disorders. You got to be able to see the plants to do that. But after that, it's just the efficiency of the light. If you search for Design Light Consortium on the internet, the acronym is DLC, that is an independent company that has now been listing many lights from many manufacturers and their test results from independent test laboratories for the efficiency of the light. The unit for light efficiency, I'm running out of room, is, put this over here, is micromoles of photons out per joule of electricity in. The really efficient lights, LEDs, are now getting up to 2.5 micromoles per joule and even higher than that. They're incredibly efficient. 10 years ago, we were half of that efficiency for lights. But it's critical to get an efficient light and a broad spectrum light so you can get enough colors to see the plants. Thanks for listening.